So I apologize, my other video got cut off, so I'm just going to continue this video. So it's in two parts. So we were done with F, we were starting E. One of the strategies that we used during our derivative process was to separate. So that's one thing that I can do here. Get a thinner pen. Okay, that's better. And of course, in addition to that, I'd want to write this as x to the 1/2. Okay. Still not in the form that I can use to use my basic power rule, as number 6 says. So again, what I'd want to do is get and simplify that. So x over x to the 1/2. Remember, when we're dividing, we subtract our exponent, so we get x to the positive 1/2 here. And on the next one, I want to bring it up as x to the negative 1/2 dx. And now it's in the form that I need, so all I'm going to do is take the antiderivative. Okay. So when I do that and add 1, so x to the 1/2, 1/2 plus 1 will give us 3/2. Divide by that new exponent, plus x, when I add 1, I get a positive 1/2, divided by 1/2 exponent, and not dx, plus c. And then, of course, I'd want to rewrite. So dividing by a fraction, we're going to be multiplying by the reciprocal, putting it back into root form, so square root of x cubed, plus 2 reciprocal of 1/2, square root of x to the first, and then plus c. So that's kind of what the antiderivative process looks like. Now let's look at some of the other functions that we know derivatives of. So for instance, like our trig functions. So what did we have to take the derivative of to get cosine x? Well, that would be sine x. And of course, plus c just in case. If we think about the sine of x, what do we take the derivative to get sine of x? And this is where it gets a little tricky, because when we take the derivative of cosine, we get negative sine because it changes sign. So going backwards, sine, we actually get negative cosine of x. I keep putting dx, and that's not what I mean. Plus c. So that's a little bit different than we're used to. But with trig, we always have to think of what do we take the derivative to get this. For cosecant squared, we get negative cotangent x plus c. Secant, we get tangent x. Or sorry, secant squared, we get tangent x plus c. Cosecant and cotangent, we get negative cosecant x plus c. And for secant tangent, we get secant x plus c. So with the derivative process, if it started in c, it negated. With the integral process, if it ends in c, it's negated. Kind of the opposite, because remember, we're just doing the opposite of our derivative process. So if we think of this in the example below, a, remember one of the rules was we could take out the coefficient. Coefficients don't really do anything until we multiply them or something. So we just bring them along for the ride, just like with derivatives. So bringing down that 2, and the derivative of sine gave us a negative cosine plus c. And then, of course, to simplify that, just remember that negative is not attached to the cosine, it's attached to that coefficient of 1. So negative 1 times 2 gives us negative 2 cosine x plus c. Sine of x over cosine squared x, again, that's not something I can do, but I'm going to use some trig things and kind of move stuff around, just like we did with trig identities in pre-cal. One of the strategies goes back to what I said earlier, is we can take this and separate it. If we think of that. And knowing some things about trig, we know sine over cosine is tangent, and 1 over cosine is secant. And if you think about it, it goes back to that one right there. Even though it's secant tangent, tangent secant is the same thing because when we're multiplying, order doesn't matter. So we wind up getting back to secant x plus c. So anytime I'm dealing with trig and it's not something I recognize right off the bat, I want to kind of rewrite it to get it in a form that I do recognize, just like we did with identities. Okay, so of course, more practice on trig to come. We know how we all love trig. Okay, that leads us to our next two integrals really quickly. So we know that the derivative of, with respect to x, of e to the x gives us e to the x, which means if I take the antiderivative of e to the x, I get back to the same thing. Even in the integral process, e to the x does not change. E to the x stays e to the x, and then of course a plus c for that integration. Okay. Now, if we integrate 1 over x, so if we think about it really quickly, so 1 over x dx, what we would do is we would bring up the x, okay, and then we do our power rule. We add 1, give a 0, divide by the new, and that right there is wrong. Anytime you're dividing by 0, it's because if we think about 1 over x, that's the antiderivative of 1 over x is actually the natural log function. If we took the derivative with respect to x of natural log of x, remember we get 1 over x, u prime over u. So if we go backwards, it just makes sense that the integral or the antiderivative of 1 over x gives us natural log of x. Now the idea of absolute value. The absolute value bars are necessary. Okay. So whatever comes after the log and the integration process, the antiderivative process needs some absolute value. Okay, and the reason for that, these are necessary. Since the domain, if we think of the domain of the natural log function, oh my god, sorry, making some mistakes. It's too early in the morning. If we think of the function of the natural log, the domain is x greater than 0. Remember, what comes after the natural log has to be positive. And if we think of the graph of the natural log function, it looks like that. Our domain is all positive real numbers, excluding 0. So the absolute value ensures that we get all positive values behind the natural log. That's a really important thing. Okay, so let's do 2 examples of where these would come into play. So if we think about this one, again, one of the things that I'm going to do right off the bat is separate. Okay, I'm going to simplify. So I get x just here, x squared over x gives us x, and then plus, we can think of this as 4 times 1 over x dx. Okay, I know that seems weird, but the reason I'm doing that is because we have a rule that says, and I'm going to separate my integrals. Okay, I have a rule that says I can separate sum and I can pull out a coefficient. Okay, again, this is not something I'd expect you to do for every single one of these problems. I'm just showing you why the answer is going to be the answer, is because of these rules come into play. Okay, so here we would take the antiderivative of x squared over 2 plus the coefficient of 4, and then the integral of 1 over x gives us the natural log of x dx. I keep doing that. Okay, sorry, plus c. Only thing I'd want to do to rewrite that is put 1/2 in front, because I like my coefficients in front. And there we go. And there's my answer. Okay, the next one, I'm going to come down here. Again, I wrote too much. If I take a 5 out, integral e to the x dx, I know 5 is a coefficient, so I'm just going to bring it down. The integral of e to the x gives us e to the x, and then of course a plus c at the end. Okay. So go ahead, if you have any questions, write them down, and on Monday morning I will address any of those questions. Enjoy the rest of your weekend.